All right, I got my timer going here. So slight change here. So this is looking at how do we deal with computation and communication APIs together. In OFI terms, we call this XPU. The easiest way to think of it, if you're not familiar with this, is like a GPU. How do we use GPU APIs in conjunction with libfabric? And same disclaimer as before, this is focused on really how do we enable the technology, and I'm not looking at how effective are any of these solutions. So we want to be able to basically enable as much as we can, and then let the applications figure out how to use those the best way that they can make use of it. So for the introduction, I want to walk back through is libfabric has what we call heterogeneous memory support. Touch on that very quickly, and then what does that mean relative to computational awareness? So the heterogeneous memory gives us data awareness, and what does it mean when we talk about computational awareness, or when I talk about it? And then for the NIC XPU coordination, so how do we, like a NIC GPU, in this case, the XPU could be the CPU, it could be an FPGA. Again, the easy model to think of is just like a NIC with a GPU. I have several workflow models to walk through. And then out of that, looking at really two different aspects of how this coordination could work. One is the XPU initiating the communication, and the other is the NIC initiating the computation. And I'll explain what both of those are a little bit later. So the XPU initiated communication is one that more people may be familiar with. And then again, coming back is based on what we have with the APIs. What restrictions do we have on the use here? How do we relax those restrictions, and what are some changes that we want to explore in terms of making the API more useful for the applications? So heterogeneous memory support in libfabric. So here's kind of a very conceptual software model. At the top, what I wanted to put was, here's like a framework based to do computation, 1CCL, nickel. Underneath that, you may have some sort of communication framework. In this case, it could be SHMEM, not shared memory, but SHMEM, could be MPI. And then further down, what I have listed here is the computational library and then the communication library. And these are my terms, not like industry terms as far as I know. So examples for the computational library, CUDA, One API Level 0, Rocker, Synapse, and Neuron. So these are the computational libraries that currently libfabric is aware of. So libfabric knows about these 5 different API libraries, and they're available. And what I'm looking for with heterogeneous memory is basically direct data access and placement. So wherever the data is located, in this case, this could be an XPU, could be a GPU here. I want to access the data directly where it's at, whether it's in host memory or device memory. And the setup for this is our upstream solution is DMA buff, which has been called out in the chat earlier. So the DMA buff becomes kind of the link between the communication library and the computational library. So as long as both of these support DMA buff, then we have a generic way of kind of set up this remote DMA so that this NIC can access the data. If the computational library doesn't support DMA buff, then it requires some sort of proprietary out-of-tree type solution that needs to be dealt with. So one of the things I want to stress here is these are all different APIs. They evolve independently, but they're frequently used together. And there needs to be a way to compose all these different APIs, libraries, together by a single application to make these transfers efficient. So what does computational awareness mean here? Again, I've simplified the flow from the previous diagram. And what we want to look here is I want to correspond where the execution occurs. So it's not just that I'm trying to place the data, like I'm not just trying to get the data off of a GPU and out to the network, or have the data come from the network and land in the GPU. I want the notification to actually go to where that computation is going to execute on the data. So an example here, the framework submits some work, schedules some work that runs on the GPU. The results come back up to the middleware framework. The middleware framework in this case is running on the CPU, on the host, right? And this return path, this number 3, the results having to come back up before it can come back down, send the results through libfabric, That's going to queue to send at the NIC. We still avoid the data copies in some cases because we have this direct memory access, but we have this latency path where we have to come back up from the GPU up to the host. And I mentioned before, so here's the two optimizations we're looking at. One of these we have kind of defined in the fabric, the other one we still don't. But the Xpu Initiated Communication, I want the XPU, when it's done, to just tell the NIC to send the data. And the next thing is the NIC to initiate the compute. So the reverse flow here, if I have data coming from the NIC and dropping into the XPU, I want the NIC to basically tell the XPU or the GPU here to say, you have the data, start, right? I don't need the NIC to have the reverse flow, right? The NIC tell the fabric, that tells the host, and then to have the path come back down. So slightly more abstract. So here are the workflows, kind of showing what I'm looking at for this. As in this case, I've defined it as I have something doing compute, something doing communication, and then I have some manager who's overflowing or overseeing the whole flow of this operation. Now, if it helps, you can think, the communication, this is the NIC, the computation, this could be a GPU, and the manager, this could be your host CPU. There's no requirement here. These could all be on the same, right? The manager could be host CPU, computation could be on host CPU, the communication could be host CPU, right? So this could be shared memory. I may just be running on a node that just have a CPU and I'm doing the computation there, right? So I'm showing these as separate pieces. They don't have to be on separate hardware. The example here is just showing how this is one way you might be thinking of it though. So the top part is looking at transmit, the bottom part's looking at receive. For the transmit side, here what I have is the manager tells the computation part to do process of some data. The results come back, and then the manager sends the results to the communication side, which then goes out. So again, the example here, I have a GPU and a standard NIC. Again, with the RDMA type NIC, process changes just a little bit. So I process the results. Here, rather than the results going back, the compute just needs to say I'm done. It's just some sort of signal coming back to the manager saying I'm done. And then the manager can say send the results, and then the communication is going to fetch the results from the computation side, like the XPU or the GPU, and just send the results out. So we don't have the data actually flowing back. We have the NIC directly accessing it. The bottom part's showing kind of a reverse flow with the receive side. And here, the receive doesn't necessarily mean it's a receive, like a message receive. The receive could be set up an RMA operation, but basically prepare to receive data from the network. Whether the data comes in as a message, a tagged message, or an RDMA write, it doesn't matter, at least conceptually for this flow. So the manager is going to prepare the communication side to receive the data. The data comes in, data lands back up to the manager, and then the manager passes it back down. Again, this is kind of a standard NIC with the GPU. I don't have heterogeneous memory support here. The data is just flowing directly into host memory and then getting pushed back down. In the bottom right here, I'm adding again the RDMA NIC. So now the data is going to be placed directly where it needs to go. But I still have the notification going up to the manager and then the manager initiating the processing. So the last workflow slide. So here, what I'm looking at is let's say the communication and computation are really the same library. Now, for example, I have a GPU with an integrated NIC, right? So in that case, the integrated NIC, I don't have to talk necessarily to a communication library to be able to send data. I can talk directly to whatever this other computation communication library is, right? This could be CUDA, this could be one API level 0, but this has the ability to basically send the data directly. Maybe I'm sending the data not over a network, but just to a peer device. So I have a backend fabric that connects the GPUs together, and I just need to send it from my local device to a device that's connected and being used by another process. So the flows look basically the same as what we had on the previous slide. Back up here, you can see process, results, and results. Process, in this case, we can say we're done, send results, and the results go out. So it's a very similar flow to what we had before. In this case, the manager has specifically waited. It wants to know when the process is done, and then it's going to send the results later. Maybe the manager needs to coordinate with the recipient to make sure the recipient's ready to receive the data. Whereas in the top right case here, the manager basically says process, and then the receiver's already ready. So process, and as soon as you're done, send the results. So this layer, the communication computation layer, sends the results and then just says, yes, I'm done. And that moves out. And the bottom ones are the receive side. Again, combined model, but back up. So it's going to look very similar to both of these flows. It's just those two boxes get merged together. So do the receive, data comes in, lets it know it's done. Then in this case, the manager is waiting for maybe several received messages to come in. Once they're all there, then it's going to say process the data. So if we look at the workflows, I took kind of what I looked at as extremes. In this case, a transmit side where I have like a GPU and a standard NIC. And then on the right-hand side, I have a GPU and an integrated NIC. I'm talking to really one piece. And what I would like to get from this is a common model that works over both of these types of workflows. So the application doesn't have to change when they're dealing with an integrated NIC versus compute and the NIC being separate. So the challenge here is, can we find a solution that works without assuming the hardware on either side? So I don't know if I'm the integrated NIC or not, or I'm separate. And then the critical challenge is, can I define APIs that an actual human, so can a carbon-based life form figure out how to use these APIs? So again, the two models I looked at, there was Xpu Initiated Communication, and then there was NIC Initiated Computation. So this is looking at the first one of those, the Xpu Initiated Communication. So conceptually, here's my abstract model here. Say, okay, conceptually, I have a NIC, I have a command queue, I write a command to the queue, and then I come down and ring a doorbell. Right, so this is a very high-level, simple model. It's not practical, right? If this is the way all NICs were designed, this would be great, but that's not the way all NICs are designed. So if we look at a NIC in a little more detail than this, our command queue, the elements may be variable size. We have several NICs that do that. So we may have there may be a command queue that are a fixed size. We have command queues that are variable size commands. There may be special flags in these commands, like a valid flag. Until this flag is set, this command is not considered done, right? We set the valid flag. Once this flag is set, then this whole command needs to be formatted correctly. Other things that can happen, the NIC doesn't have to wait for the doorbell. So the NIC can read ahead, can take a doorbell and then start reading ahead and saying, okay, the valid flag is set, valid flag is set, valid flag is set. Take these three commands and pull them down immediately. And there may be other parts of the NIC behind this. Maybe there's a count of how many entries are valid that it's tracking. And when we looked at this, the details as to how this was done was NIC specific. So it's not even vendor specific, but a single vendor could have 3 or 4 different ways of how they implemented the NIC and how these command queues and doorbells and everything would fit together. So we wanted to have a Xpu Initiated Communication, but right, we were dealing with this fairly complex type of NIC setup. But I want to start with the simple model. So in this case, I want to try to build the API around a simple model, and can I capture the complexity that we need here on the right-hand side? So for anybody following libfabric, we have what we call Xpu Initiated Communication. It's Xpu Triggered Ops. So we defined a set of operations that requires the XPU to actually trigger them. And this combines essentially the triggered operations that we had in libfabric with the heterogeneous memory APIs. So the kind of the way that works is like the framework would say prepare a send. libfabric would prepare the send. That's going to post some sort of, say, deferred send to the NIC. So it prepares what the send will look like, but it doesn't actually start it. And then as part of the trigger, the middleware is going to tell us, say, a compute library, say, here, do the work that it needs to do, and then here's the way to trigger. So here's a notify that you need to perform. And then on the GPU side, it's going to do the work, and then it's going to do this notify type operation. And that notify will basically signal to the NIC that the data is ready for transfer. We make the libfabric provider perform the setup. So this, whatever this notify is, that's up to the libfabric provider to specify. And it knows that the notify, as part of the send call, is going to know which compute library and device it's dealing with. So if this is a deferred send, it knows, am I dealing with CUDA over here? Am I doing with one API? Am I doing with Rocker? But it knows what this compute library is, and then it can use, like, for example, DMA buff to do the setup, so that this GPU can actually do this notify call. But it does have some requirements on what this the compute library must be able to do. Check time. So here's kind of what it looks like in the code spot. It is a fairly universal triggering mechanism. So there are a lot of NIC implementations. We've tried to map this over, and we are working through proof of concepts to show that it's working on a couple of vendors here. But in this case, what we're doing with the application calls write message, they have a trigger type flag that they specify, and the trigger becomes an XPU triggered. So this data structure is what the application is going to end up filling out. And here is where the XPU is specified. So this is where the heterogeneous memory interface feeds into this. So we know which library we're working with here. We may know which device we're working with. I left out some of the fields on this to keep it simple, but basically where we're going with the triggering. And then the trigger itself is an array of variables. So we have an account, that's the number of entries in the array, and then we have this array here, which is going to be this structure on the right-hand side. In most cases, we expect that a provider will have probably maybe 2 or 3 of these variables in their array. Nothing super complex, but this does allow for an arbitrary number of fairly complex variables. So the variable, the data type, this is similar to what we use for atomics and collectives. The data type is going to be like, am I dealing with an int 8, 16, 32, or 64-bit integer value? And based on the data type is which one of these values is actually useful. And we do allow a more complex data type where, like, the data type could be an array. So this could be an array, and in the array case, the data would be off of this pointer, and then we'd have a count for the number of bytes. So in the best case, a provider can maybe have, say, just ring the doorbell, right? The application said write message. The provider has formatted that command, and this simply says, here is my one place to ring the doorbell, and the doorbell may be a 32-bit value. So all we need from the GPU side is the ability to say write 32 bytes, or sorry, write 32 bits. Right, so we don't need much help from the GPU side, but it does have to have some command that says write a 32-bit value, and that write has to be able to cross, possibly across PCI. This may be host memory. This could be on the NIC. If it's on the NIC, then again, it's going to be the responsibility of our provider to basically do the mapping here so that the address is accessible from the device. In a more complex case, this variable could be the whole command, right? We could send back, here's the data, here's an array, the count is maybe 64 bytes. I have a 64 bytes worth of data I need you to write. So now I'm going to write the whole command from the GPU. But it doesn't have to know what the command format is, it just has to, I'm writing 64 bytes of data. And then if I had a second variable, I could have the first variable be the command, and then the second variable again be like a doorbell. To actually trigger the NIC to go look for the command. And I'll come back to, there's some problems with that model. So this model, is in libfabric today. Again, there are going to be some slight issues with this we'll talk about. But going to the next optimizations, a NIC initiated computation. And what you'd really want here is, data comes in, the NIC's going to write an entry to a completion queue, and we want this entry to basically signal the GPU to say, okay, I've received the data, signal the GPU, and now it can start. problem with this one is this model's, again, not viable. So first we have several command queues, typically. So maybe one queue pair per peer we're talking to. These are all feeding into a completion queue. We don't know which entry in the completion queue matches with the specific data we're looking for. So it's not easy for us to know from the provider to say, yeah, this entry here, the fourth one down, is going to be the completion for the receive that has the data you're actually needing. So it's very hard to know this when you have several command queues feeding into one completion queue. Any errors basically blow up this whole process. And then the other problem we have is a lot of these are using RDMA. So we're receiving the data, large transfers through RDMA writes that'll go directly into, say, the GPU memory. Well, RDMA writes don't generate completions at the target. We'd have to use like a write with immediate data or something, which may not be supported by the underlying hardware. For example, iWarp doesn't necessarily have the CQ data. So this model kind of falls apart as to the complexity here on the right, not something we want to be able to expose to an application. So it's something we can really do here on the left to try to build a model. So our phase one solution for now is we're punting. Saying, okay, well, what could the app do? If we didn't have anything in libfabric for this, what would the app have to do? So in this case, the manager coordinates transfer with the peer, then sets up the computation. Well, one thing the application could do is, say the data does an RDMA write, so the data could come in through the communication stack, get dumped over into the device memory, and then have a second RDMA write that's basically the signal. Or if we needed to, the second write, this could be an atomic. So if we have, it could be an atomic add, and this add could be modifying device memory. So now all we need from the computation side is the compute side has to basically just wait for the signal to change. Maybe this signal is a byte, maybe it's 4 bytes, or maybe this is an atomic operation, and it just needs to wait for the atomic value to be set to, 10 or 20 or however many peers data it needs to wait for. So with this model, it should work with both standard offload NICs, so whether or not we have direct data placement or not, or we're going back through the manager and dropping the data in. Either way, it could work. The signal, basically the computation would have to wait until the signal arrives. And what we need from the XPU is basically the XPU needs some ability to pull on a local memory change. So that's what we need from the Xpu API side, is before it starts processing, it needs to be able to basically check a memory value to change or to reach some other specific value. So if we leave it up to the application in that case, the question is that efficient enough? Is there anything we can really do at a lower level for that? So other thoughts on those two solutions? So first, we have this Xpu Triggerable operation. One, we defined the API that the endpoint, we can't share it with the host. So we can't have a queue pair, for example, where the host is writing to the queue pair and the GPU is writing to the queue pair. That's defined just so it's easy for the provider to actually implement this, and so it can work. So that does increase resources for the on the NIC side. The other restriction is that these triggers basically have to be in order. So every time that the application posts this Xpu Triggerable operation, it's going to get back these list of variables, right? Those variables are mapping, say, to command queues, entries. And the only way for this to work is if every one of those variables is written in order according to how the application has posted, say, the write message or the sends. So it has to do those in order. So there's no out of ordering can occur, even if the GPU and the NIC could support an out of order signaling. It doesn't mean it necessarily will be processed in that order. Again, because we may have like these valid flags in the commands, and we have to wait for the first one at the front of the queue to actually have the valid flag set, or the NIC's not going to even start processing. For the NIC Initiated Computation. So one requirement we have based on the solution I was showing is we do require write after write ordering, or an atomic after write ordering. The alternative to that is the peer. So again, we're pushing it up to the application. It has to do a write, wait for a completion on that write, and then it can do the second write that does the signaling. And I don't have a lot of help here. Like, we might need new network protocols to make this more efficient. So how do we get rid of, say, write after write ordering? How do we allow out of ordering without introducing this delay of writing the signal until the first write completes? All right, this is where I'm talking about a write plus an atomic add. Now I want to be able to place the data, and after the data is placed, I want to go increment a value so that the GPU can actually check that value. Right, but that again requires new network protocols. You require new hardware in order to make this more efficient. Otherwise, the worst case is you don't have write after write ordering. You do the write, wait for completion, and then do the second write. And almost out of time. Okay. So for how do we handle, let's say, triggering out of order? And this is one of the exploration things I had is can we define a transmit window? So in this case, my command queue, I have 4 entries. Can I define a window here? This is, okay, here's my window where I can write commands. And then a variable becomes relative to that window. So the variable says, okay, here's the window I'm dealing with. I'm dealing with, this first window. Here, my window might be a command queue. The doorbell could be a separate window. I could have an offset and then an increment to the window when I'm done. So I have the same sort of variable. So in this case, my simple example, I'm doing a mem copy. So to write a variable, I start at the window base. I have an offset. This could be 0 if I'm just writing a new command, right? I'm going to write the data and the size. And then the window increment tells me how I update the window after I've written. That was kind of fast, but basically it would allow these commands to be written in any order. Well, the application could do any of these variables in any order by simply having to have the first variable would fill the first window, the first part of the window, and then the window would be incremented. So the base would be incremented based on which variable was written. And then the next variable would fill up the next command. So this becomes a way for the application to write basically these commands in the order as they're ready to be posted. And for NIC-initiated computation, I have nothing. So I don't know what else we can do with that other than punt to the application. So this is an area we'd have to explore more on. And that is it.
Very cool. Thank you, Sean, for both presentations. Are there any questions for Sean on either presentation? We have just about time to start the next one, but anyone has any questions? If not, we can. Oh, we do have a question. Are you considering a design where the XPU directly submits a command to the NIC versus ringing the doorbell to trigger an already posted command?
Yeah, so the XPU triggered API that we have actually already allows that. So one of the trigger itself is a variable sized amount of space, and that could be the actual command. So it could be the variable would be write a command, and the second variable could be ring a doorbell. What it is requiring is that the provider is going to set up the format for the command.
Any other questions or comments?
And then the last slide I was talking about there was, can we get these commands submitted out of order? Well, in order as they're ready to be submitted.
Okay. And one final question before we move on. Does that mean that we need a libfabric stub for each programming model?
I don't know what you mean with that, Brian.
Well, maybe we can discuss that offline. Okay, thank you, Sean. I appreciate both the presentation. Nice talk as always.